Hello everyone. Hope you are doing good. So last day we are done with the variation of the conductivity and molar conductivity for the strong electrolytes and weak electrolytes, and we had discussed about the limiting molar conductivity or molar conductivity at infinite dilution. Okay, and we had seen that from the graphical representation, we can very easily find out the value of the lambda 0 for the strong electrolytes by using the Kohlraush equation, because it's a straight line. So by extrapolating it wherever it cuts the y-axis, we are going to get the value of lambda 0. But that for the weak electrolytes are not possible to extract, right? Because the curve is parallel to the y-axis, so by extrapolating we cannot get it. So the question that is in our mind now is that how can we find out the value of lambda 0 for weak electrolytes? For weak electrolytes, how can we do it? If you can remember, the graph for that was, if we plot lambda versus root c for the strong electrolyte, it is like this, and for the weak electrolytes it is like this. Okay, so for strong electrolytes it is this, and for the weak electrolytes it is this, but we cannot find out it. For the strong electrolytes we can get it by extrapolation, but for the weak electrolytes we cannot get it, because if we extrapolate it, it is never going to cut the y-axis. Okay, so that we know. Then how can we find out the value of the lambda 0 for the weak electrolyte? Here comes a lot of experiments done by Kohlraush. Please don't go in the values. I am not going to write down the correct values. Neither you have to know the correct values. Just understand the concept. Just understand the concept. Whatever values are there, the values will be given and we can use that values. What he did actually, he calculated the lambda 0 values for lot of strong electrolytes. Lots of strong electrolytes. Okay. And what he found very surprisingly is this. See, suppose what he found the lambda 0 value for sodium chloride. He found the lambda 0 value for potassium chloride. These are all different values. Suppose this is 10, this is 7. Okay. He found the lambda 0 value for sodium bromide. He found the lambda 0 value for sodium bromide. Suppose that is equal to 17. Okay. He found the lambda 0 value for potassium bromide. Lambda 0 value for potassium bromide, KBr. Okay. And he found the value equal to 14. Like that he found so many. Okay. Other ways I am just writing over here also. He found the value of sodium chloride. Lambda 0 value for sodium chloride, as I told. Sodium chloride is how much? 10. Suppose, no, not 10, just suppose. It's not that it has to be same only, I'm just telling it. He found the lambda 0 values for the lambda 0 value for sodium bromide. Let me write it from those values only. Lambda 0 value for sodium bromide, he found 17. Okay, he found 17. Lambda 0 value for sodium chloride, he found 10. Okay. Lambda 0 value for potassium bromide, he found how much it was? 14. Okay. These values are certainly not correct values, and I am just writing it for your understanding, nothing else. Whatever values, that is not all looked after. And lambda 0 values for the potassium chloride, sodium bromide, potassium bromide. This is sodium bromide, sodium chloride, sodium bromide, sodium chloride. This is potassium bromide and potassium chloride. Potassium chloride he found as 7. Let's see, these are the values he found. Obviously, I wrote in a different manner. Why did I write in a different manner? Only 4 values only I had written. You see it, if I subtract this from this, means lambda 0 sodium chloride minus lambda 0 potassium chloride, we are getting it is equal to 3, right? 10 minus 7, 3. Yes. If we get it subtracted from this to this, and this from this, whether lambda 0 sodium bromide minus lambda 0 bromide, then also we are going to get it as 3. Means with subtraction, these values are all different, but the difference between this and the difference between this is same. Yes. Now come over here. These values are all different, but if we see the difference between lambda 0 sodium bromide and lambda 0 sodium chloride, it is coming at how much? It is coming at 7, right? 17 minus 10, 7. Here also lambda 0 potassium bromide minus lambda 0 Potassium chloride is also coming as 7. So the values are all different, but certain differences are same. Why so? He was there. Obviously, this is only 4 examples I have taken. He had done with lots and lots of electrolytes, strong electrolytes, and we found the same trend, exactly same trend. Okay, and then he concluded, and he could explain these facts that lambda 0, that is the limiting molar conductivity of sodium chloride or potassium chloride or any strong electrolyte, or rather any electrolyte, is not because of the molecule. It is not because of sodium chloride. It's not because of the molecule. It's not because of sodium chloride or potassium chloride or sodium bromide or potassium bromide. It's because of their individual ions. It's the contribution by the individual ions. That means it is because of sodium ion and because of chloride ion. Because they are migrating, they are moving individually. They are moving individually and independently. Okay? And hence he proposed a law which is known as, and we can very easily explain this now, and hence it is known as Kohlraush's law of independent migration. Independent migration means what? Means that the limiting molar conductivity of a strong or weak whatever electrolyte is nothing but the summation of the limiting molar conductivity of the corresponding ions. Okay, whatever ions are present in that, it is the summation of those limiting molar conductivities is the molar conductivity of the electrolyte. So you can write it like this. Suppose for sodium chloride, if I write lambda 0 for sodium chloride, we write it as lambda 0. This lambda for the ions we write small. Okay, limiting molar conductivity. Lambda 0 for sodium plus lambda 0 for Cl minus. Okay, so if I now try to write lambda 0 for potassium bromide, it will be lambda 0 for lambda 0 K positive plus lambda 0 Cl negative, right? Lambda 0 for K positive plus lambda 0 for the Cl negative. Okay, like that. If I just ask you that what is the lambda 0 value for the barium chloride, suppose barium chloride. Okay, I'm talking of barium chloride. Suppose lambda 0 value for the barium chloride. So barium chloride, what are the ions that is present in barium chloride? Lambda 0, how barium chloride is dissociated, we must understand that. How barium chloride is dissociated? BaCl2 is dissociated as Ba2 plus 2Cl minus. So it is dissociated into 3 ions, right? 1 barium ion and 2 chloride ions, and all will individually be contributing to the lambda 0 value of BaCl2. So can I write lambda 0 for BaCl2? Lambda 0 for BaCl2 is equal to lambda 0 for Ba2 positive for the barium ion plus 2 of lambda 0 for Cl negative, that is lambda 0 Cl negative plus lambda 0 Cl negative. Yes? Okay? Did you get it? Very good. So in general, can I write, suppose electrolyte is like this. Suppose electrolyte is like this. Okay? An electrolyte is like this. AXBY. In general, an electrolyte is like this. So how it is dissociated? It is dissociated as how many A's are there? X's are there. And what is its charge? Its charge is Y positive, right? Its charge is Y positive. And how many B's are there? Y B's are there. And what is its charge? X negative, right? So that is how it is dissociated. So if I write lambda 0 for AXBY, lambda 0 for AXBY should be equal to X number of AY positives lambda 0. That means X of lambda 0 for AY positive. Yes? Okay. X lambda 0 for AY positive plus how many BX negative are there? Y of them are there. So Y lambda 0 for BY negative. Is it clear? Sorry, BX negative. BX negative. Is that the general expression of the Kohlraush's law of independent migration? That is what is Kohlraush's law of independent migration. That is, individual ions present in an electrolyte are responsible or are contributing to the total molar conductivity of the electrolyte. Bas, that's all. Okay, fine. Now, depending on the nature of the electrolytes, depending on the nature of that, simple also, you must know this point also, depending on the nature of the electrolytes can be classified in different types. Kaise? For example, suppose sodium chloride. Sodium chloride. It is dissociated as, you know, Na plus Cl minus. So the charge of the positive ion is 1. Charge of the negative ion is also 1. Okay. This type of electrolytes are called 1:1 electrolyte. These are called 1:1 electrolyte. So what about BaCl2? BaCl2, the charge of the positive ion is 2. And the charge of the negative ion is -1, is -1 or 1. Okay. So this is the type of electrolyte. What type? 2:1 type. Suppose if I take like this, Na2SO4. So how Na2SO4 is dissociated? 2 Na plus SO4 2 minus. What is the charge of the positive ion? The charge of the positive ion is 1. And what is the charge of the negative ion? Charge of the negative ion is 2. So it is a 1:2 type. Okay. So like that we can differentiate the electrolytes depending on the number of the positive charge and number of the negative charge. Now our intention was, we started this class by saying that how can we find out the lambda 0 value of the weak electrolytes. We can find the lambda 0 values of the strong electrolytes by extrapolating. There is no question about that. But how can we find out that for the weak electrolytes? Can we find out, just think, can we find out by using this particular principle, this particular law, Kohlraush's law of independent migration? I think we can do. Let us try this. Suppose you have to find out again, the values, don't go in the values. Simply don't go in the values. Whatever values I am writing, whatever is coming in mind I am writing. That is nothing to do with the values. Okay. So you have to find out lambda 0 for CH3COOH. Obviously this is a weak electrolyte, all of you know. We have to find it out. We cannot get the value directly by extrapolating it. Yes. But can we get the value of lambda 0 for HCl? Because it's a strong electrolyte. Suppose lambda 0 for HCl is 5. Just suppose lambda 0 for HCl is 5. Can we get the value of lambda 0 for NaCl? That is also a strong electrolyte. Yes, we can get this value also. Suppose that is equal to 7. Suppose that is equal to 7. Okay. And can we find out the value of lambda 0 for CH3COONA, that is sodium acetate, that is also a strong electrolyte. Sodium acetate is also sodium salt. All sodium salts are strong electrolytes. On the sodium acetate, suppose the value is 10. By knowing these three values, can we find out the value of lambda 0 for CH3COH by using the Kohlraush's law of independent migration? See, it's very simple. What is this? What is lambda 0 HCl? It is nothing but lambda 0 for H positive plus lambda 0 for Cl negative according to Kohlraush's law of independent migration. This is nothing but lambda 0 for Na positive and lambda 0 for Cl negative. Yes, according to the law. And this is nothing but lambda 0 for H positive plus lambda 0, sorry, H negative, okay? Na. Okay, lambda 0 for Na positive plus lambda 0 for CH3COO negative. That is how it is dissociated. CH3COO negative plus Na positive. These values we know. We know these values. Clear? And what we have to find out, lambda 0 for CH3COOH we have to find out, which is nothing but actually lambda 0 for H positive, CH3CO negative plus H positive, right? Okay, lambda 0 for H positive plus lambda 0 for CH3COO negative. That is what we are going to find out. If we find out that, then only we are finding out the lambda 0 for CH3COH. Let us see. H positive. How, from where we will get H positive? From here. So I am writing it over here. Just lambda 0 for equal to lambda 0 for H positive plus lambda 0 for Cl negative. We know this. We know this value. Lambda 0 for H positive plus lambda 0 for Cl negative means nothing but lambda 0 for HCl. That we know. This is nothing but lambda 0 for HCl. And we got H positive. H positive we got. Okay. Now we have to get CH3CO negative. कहाँ पे है? It's here. Okay. It's here. So plus. Can I write lambda 0 for Na positive, lambda 0 for Na positive plus lambda 0 for CH3COO negative. Okay, that is nothing but lambda 0 for CH3COO Na. Yes, so we got H positive, we got CH3CO negative also, but along with that we got extra what? Extra lambda 0 Cl negative we got, extra lambda 0 Na positive we got. So I'll write minus this plus this we got minus. Now Na positive and Cl negative has to be subtracted. So can I write minus lambda 0 for Na positive plus, obviously we are writing in bracket, plus lambda 0 for Cl negative, and that is nothing but lambda 0 for NaCl. Can I write this? Can I write this? So what is lambda 0 for CH3COH actually? It's nothing but lambda 0 for HCl. Can I write it? Lambda 0 for HCl plus lambda 0 for CH3COO Na. Yes, minus lambda 0 for NaCl. Is it that? Is it that? It is nothing but that. That is what is lambda 0 for CH3COH. Okay. And what is the value? All the values we know. Lambda 0 of HCl is how much I told? 5 plus what is the value of lambda 0 for CH3CONA? 10. Okay. Minus lambda 0 for NaCl is 7. So that is equal to 15 minus 7. That is equal to 8. So the value of lambda 0 for CH3COH you can very easily find out equal to 8. So can I conclude to the fact that the value of the weak electrolytes, I mean the lambda 0 values of the weak electrolytes can be found or can be obtained, can be determined from the values of the lambda 0 values of the strong electrolytes, lambda 0 values of the strong electrolytes by using Kohlraush's law of independent migration. Is it clear? So everything is clear about lambda 0. Yes? So the basic part with the molar conductivity things we had finished. Next day we are going to start with cell. What is cell? Two types of cells. Slowly we are going to learn, but first of all I will recap today's class and then I will end the class. Okay. What did we study? We started with saying that we know how to find out the value of lambda 0 for the strong electrolytes directly from the graph or from the graphical representation, but we cannot find it for the weak electrolytes. So how to get it? Okay, then again Kohlraush came in the picture and he did a lot of experiments, and from there he found that the value of lambda 0 of the electrolytes is nothing but the indivisible contribution of the ions, and that particular principle or that particular law is known as Kohlraush's law of independent migration, because independently the ions are migrating, and that is why they are contributing to the molar conductivity or limiting molar conductivity of the electrolyte. By using that particular rule or by using that particular law only from the values of the strong electrolytes, we can very easily find out the value of the weak electrolyte by using the Kohlraush's law of independent migration. We had seen one example, and one more point we had done is depending on the charges of the positive ion and the negative ion of the electrolytes, depending on the charges of the positive ion and negative ion of the electrolytes, they can be classified in different types like 1:1, 1:2, 2:1, 2:3, 3:2, whatever. Okay, so that depends on the charge of the positive ion and charge of the negative ion. Hope you understood everything today. Okay, and we are going to continue with the sale for the next day. Okay, till then, goodbye, keep safe and keep healthy. Okay, thank you.